Good afternoon, everybody. So my name, if I may start, so my name is Raphael Frank. I am a research scientist at the University of Luxembourg. Very sad that we cannot meet in person in Italy because the weather in Luxembourg, as usual, is very rainy today again. So probably in Italy would be way better. Having said that, my research interests are around vehicular networks and related applications, and I'm very happy to co-chair this session with Michaele. So I hand over to you for your introduction. Okay.
Thank you, Raphael. So, hi everyone. You probably already have seen me before in this conference, but yeah, again, I'm Michele Segata. I'm currently an assistant professor at the University of Bolzano, and as Raphael, my main research area are vehicular networks, but I'm also working on wireless networks at large, so to speak. So yeah, the session we have today is kind of broad because we will be talking about vehicular, area and community networks. So let me see, do we have all the speakers? Yes, great, right? So we have Julia, and then Fabio, Anna, Anai instead of Federico, right? That's great.
Yep.
And Gabriele as well. Okay, so I will leave the floor to the authors for a round of presentation, maybe going in the same order as in the program. So Julia, if you wish.
Okay, so I'm Yulia. I just graduated from my PhD at the University of California, Los Angeles. And my research interest is in wireless mobile communication systems, including communications for autonomous vehicles.
Okay, Fabio.
Good afternoon to everyone. I'm Fabio Busacca from the University of Catania. I'm currently a PhD student at its first year. And well, at the moment I'm dealing with multi-access edge computing systems, their issues and their problems. Thank you.
Anna, do you want to reintroduce yourself or?
I already introduced myself, but I'll take the opportunity to say that there are two co-authors online, which is Antonio Rodrigues and Rui Meireles, and maybe each one can say in 15 seconds, introduce themselves.
Okay, I'll start. My name is Antonio. I'm a PhD student of Anna, and my research interests, they started with information-centric networking. Then I switched to a more practical study of wireless problems on a system level. I was first studying on how to enable fast handoffs between APs with different technologies, with heterogeneous technologies, N, AC, and AD. And this work that we'll present today is about using AD.
Yes, hello everyone. My name is Rui. I'm an assistant professor at Vassar College in New York, and I'm also interested in vehicular networks, protocols, experimental work, and all of that. Thank you.
Hi everyone, I'm Gabriele Gemmi. I'm a master's student at the University of Trento, and my research interests are wireless mesh communication and specifically wireless community network. Thanks.
So, hello everyone, I'm Anand Deshpande, and I am a first year PhD student at University of Padua, and my research focus is actually right now in routing schemes in wireless and ad hoc networks, specifically working on flying ad hoc networks right now. Overall, it's basically application of machine learning in wireless ad hoc networks, focusing on network optimization.
While we wait for questions from the audience, so we are gonna look at the chat. So if you want to ask something for the authors, as always, please write there. While we wait, Raphael, may I start with a question to bootstrap this session?
Sure, go ahead.
So yeah, as I said, this session is quite broad, but I have a general question that for sure addresses 3 out of 5 papers, but it might be interesting for the other 2 as well. So yesterday, I guess it was Giuseppe Bianchi raising the issue. We have been talking about that there's a lot of research going on millimeter wave communication, and it seems that we are having a hard time deploying them in infrastructure-based communication technologies because of their challenges. So we know it's difficult to do beam tracking. We have a lot of problems of shadowing and the like. But here we had at least 3 papers talking about the usage of millimeter wave for vehicular network or for drone-to-drone communication. And in my understanding, it looks like millimeter wave it's kind of more suited for this direct V2V or direct drone-to-drone communication. So we might have better chances there. And I would like to ask all the authors if you agree with my view, or if you do completely disagree, and whether you see other kind of challenges in this in this application.
So if I may start, like in the drone networks, we basically started off with that assumption itself, that because drone networks more than likely will have aerial communication, so it will have direct line of sight. So millimeter wave actually works well in such scenarios, as you don't have that many amount of obstacles in the path compared to, let's say, in a general cellular network scenario. So that's in that case scenario, I would actually agree that yes, millimeter wave actually works in direct drone-to-drone communication.
You still have the problem of tracking though, right?
Yeah. So we are investigating how to actually maintain communication, and we basically are going to investigate how to have persistent communications between 2 drones when they're moving in the environment, and how to actually keep the beams aligned with each other. So yeah, there are multiple problems that have still to be addressed to it, but yeah, in a blanket scenario, you can consider it a very good application of millimeter waves.
I can speak for, so in the case that I've studied, in our experiments, we actually tried to Frankenstein some AD routers into 2 vehicles. What we verified, I mean, that the challenges are the beam tracking, the movement. So one interesting application could be for when cars are moving at slow speeds. In our case, we tested it in an intersection. So there it could be for particular scenarios and use cases, it could still be an interesting way of transferring a lot of data in a short time because of the large bandwidth. But of course, tracking and distance are a challenge.
And also in highway applications, right? Where
yes,
the relative mobility
exactly.
is
If the relative movement is very short, it doesn't vary over time. That is also an interesting scenario use case. Yes.
I've seen Julia has yeah.
Yes. All right. So I have something to say. Our work has 2 networking schemes. One involves the infrastructure-aided networking scheme, and the other is vehicle-to-vehicle networking scheme. And for both schemes, the networking entities involved in a transmission, in a transmitter-receive pair is almost always adjacent to one another. So for example, when we have vehicle-to-vehicle communications, we have hop-by-hop communications between vehicles on the same lane, for example. And for vehicle-to-infrastructure communication, we have relays erected on the highway such that the infrastructure communicate to the nearest vehicle from it. So it minimizes the number of vehicles which need to have a significant beam alignment. For example, when we have vehicle-to-vehicle communications on the same lane, we can effectively regard that the vehicle-to-vehicle communication does not need significant beam alignment because they always stay on the same lane. As for vehicle-to-infrastructure and infrastructure-to-vehicle communication, I agree that there is some beam alignment which is needed to be done, but it's not as significant because the beam does not shift to different vehicles often, as within one infrastructure cell or within one RSU cell, only one vehicle is elected as a gateway relay. So we keep tracking beam alignment only with this one vehicle at each time.
Thank you for the answer. Rafael, do you have something additional to add?
Maybe a follow-up question on this, particularly for maybe for Anna's paper or any of the co-authors. So actually, I enjoyed very much reading the paper. I always like experiments. And I found it actually, I mean, these effects that you describe in the paper, that you get at a certain location, you get a much better signal now, is something that I have seen in the past also in other papers. And also when you tried to reproduce the effect with the stationary experiment, you could not really reproduce, right, the same result. So could that be due to the signal propagation in some kind of way, because you have two different environments for the mobile experiments and for the static experiment, right? So you might have different reflection of the signal, and particularly in this kind of environments and with this technology, there might be some very specific effects that are generated by the environment. What do you think about that? Could that be a possible explanation, or how do you see that?
Well, what I can say is we, in our experiments, in both experiments, we found evidence that at least that may be the case, because, for example, even in the static experiments, sometimes the simple fact of having someone moving on the side would actually cause the 2 points to start communicating with each other. So it seems that the propagation of this type of signals is very dependent on the variability of the channel conditions. So yes, and so that's what I have to say. I mean, we're currently studying that. So after noticing that that type of evidence that are a little bit they're anecdotal, because we were not doing the experiments to check the effects of people moving or the changes in the environment. But at least now, because we have that idea, it's something that we also try to incorporate in the further work that we're doing.
To complement that, the static environment it's a very, very large area, like any building or any other thing except people who pass by were more than 20 meters away. And let me put it this way, if you cannot regularly communicate at 12 meters, I would expect that anything at 20 meters is not able to reflect something.
Exactly.
However, we did observe the effect that Antonio is mentioning. And again, in the mobile experiments, we repeated them 2 weeks ago, right, Antonio, or 3?
Yes.
And exactly the same place with a high precision GPS device, and it's still there. So it's definitely something. So we can observe that consistently. And again, so it was not a one-time thing. The exact cause, I mean, we don't know if it's the lamp posts, could be, but otherwise it's still quite difficult to explain.
Another thing that could be an explanation is the radiation pattern of the devices, the particular devices that we're using. We based our analysis. So, for example, whenever we try to analyze the different sectors that each one of the devices used, we based our analysis on previous papers that shown certain radiation patterns for the same type of devices. But we don't know if these radiation patterns actually vary a lot between individual devices. So, because sometimes they do not, the sectors on which we actually get the best communication, they do not coincide with the best areas of the radiation pattern that are on those papers. So that could also be a possible explanation, but we would have to analyze our devices in order to be sure about that.
Well, thank you for this explanation. So you have some more work, some more experiments to do, and then hopefully in the next paper we will see the reason. Okay, audience, don't be shy. I mean, if you want to ask questions, chat, or even just unmute and ask the question to the authors. Otherwise, obviously, we have a couple of questions prepared. Here I have a question actually for Fabio from Gianmarco Lia. How much time did you spend for training the DNN? Have you ever thought to use a different kind of DLR? Actually, also a question that I had on my list.
Okay, that's fine. So, well, it's quite an interesting question, and well, what about using different kinds of deep reinforcement learning? Well, that's something we're looking forward to do, but well, we try to stick to model-based reinforcement learning because, well, we thought it will fit such a scenario where we will able to model the system in a proper way. But of course, well, whenever instead we have to deal with scenarios where we can't model in a proper way, in a complete way, well, I do think that, for example, resorting to other types of reinforcement learning, that is deep neural reinforcement learning, well, could be the correct choice since, well, I do think that sticking only with model-based theory is just the first brick in our wall. But in the future, where we're looking forward to instead going for totally reinforcement learning-based models, or even with hybrid models, where we can start from a model of the system not refined and then go on and refine it basing on the actual conditions of the vehicular network.
So that answered the question. Any other questions from the audience? Or maybe Michele, you might have some.
While we wait for the audience, I actually had a question for Gabriele. So just to summarize to the audience what you did, so Gabriele worked on a topology generator. As you know, when we are doing performance evaluation of networking systems, the topology that we are considering plays a gigantic role, right? If it's accurate, you might have meaningful results. Otherwise, you might just get bogus results. And what they did in their paper was to create a wireless network topology generator that also takes into account correlating shadowing, taking data from buildings and maps. Now, the question that I have for you, now I see also Leonardo popped up. Hi, Leonardo. In your paper, you said that using correlated shadowing is very important for your topology to be accurate. Can you tell us a little bit more how you took into account correlated shadowing in generating the topologies, how the process works, and what kind of data you need, and so on?
Thanks for the question. So in our work, which we call usually a topology emulator and not a generator, we actually try to connect nodes which are placed into, let's say, a real-world environment. And we do this by fetching a data set from public administration, like LiDAR data set and building data sets. And once we have these kind of data sets, we are able to place the nodes on buildings and try to connect them. Try to see if they can connect them by checking the line of sight and the Fresnel zone. So in this way, we overcome the correlated shadowing problem. But because we are actually working on real data, so we are building networks on a geographical map, and we are building them in a way that they could really exist in the real world. So this is why we could cope with this problem and do something that other generators cannot do.
And on let's say,
So
on
if I can add something,
Leonardo,
and this is
sure.
maybe also, I'm another author of the paper. I'm Leonardo Maccari, University of Venice, and this is also maybe a question for the others. What we actually wanted to do is to try to understand how can a topology that is built with line of sight communication, wireless line of sight communication on some urban or rural area can look like, and how it differs from standard topologies that you get from topology generators and random topology generators. And so actually we noticed quite a few differences, especially related to correlative shadowing and to the fact that you cannot have links as long as you want because you have obstacles in the middle. And this, we are still in the phase of trying to understand how this will impact any kind of property of a protocol or an application that you run on those networks. And so one of the questions that I have also for the others is, how do you keep this into account? So when you actually run, for instance, I don't know, you emulate your FANET network, how do you take into account the topology that may be formed, and if this somehow influences the performance of what you're actually studying? And where do you get the data? And if you think that works that can actually start from real data, from real 3D shapes of real cities, can actually help your work and improve your results somehow.
Wants to reply to Leonardo?
So in terms of like topology generator, like what we basically did in our experiments was we basically did you can say a randomized topology generator, but based on specific tracking and movement scenarios. So we basically have another work that is going on where we actually track movements of drones, and that was basically used as a data set to generate these kind of topologies. So it was a randomized position based topology which took into account you can say how many nodes are basically deployed in a certain area, but it didn't take into account the movement of it. The movement was basically generated randomly based on a certain model. So yeah, I don't know whether that answers your question or not, but yeah, I would say it's how we did it in our way. So.
But in your case, the problem is finding a movement pattern of the drones that actually makes sense, right?
Exactly. So in our scenario, we basically the drones are basically autonomously moving on their own. They're basically doing a tracking and monitoring application in a field. We basically, from a central controller, we basically tracking these movements of the drones and taking into account where they're moving on what position using Kalman filtering based tracking mechanisms. So we basically have an uncertainty for a position. So the topology that we created was based on these Kalman filter tracking. So it was slightly based on real world scenario, but a little bit more simulation based.
Maybe following, I guess it's time to wrap up, but maybe following this line, something for Julia. When reading your paper, so your paper is rather theoric, right? So what you've been considering in your case is a fixed topology, right?
Right. We are considering an autonomous vehicle scenario whereby all the vehicles have a certain predetermined distance with a parameter value which is already pre-computed to optimize certain value, let's say to maximize the throughput capacity of the system. So the topology of the system is relatively fixed, for example, between vehicles on the same lane. And whereas, let's say when we are considering vehicles on adjacent lane or another lane, there is a movement relative between the different lanes, but it's limited to just that one dimension.
Okay.
And I must say that I know that that is a problem, but we are not there yet. So it was the fact that this paper is sort of kicking some ideas on something we need to do, because we are now considering only this vehicular, this millimeter wave link is just a part of a bigger scenario, which involves also edge computing for autonomous vehicles. And the topology is an issue, how to interconnect the different technologies, but we have not picked it up yet as a problem. But probably will now that you mentioned it.
I guess it's time to wrap up. Marco popped up. So I would like to thank, well, of course, Rafael for helping me in hosting this session, and all the authors for their time for questions. So thank you to all of you.
Thank you.
Thank you also, Michele, and thank you to all the authors and all the audience for joining this session. And I wish you a good rest of the conference.